So hi and welcome everybody to the talk titled The Future of RF and Microwave Antennas for Future Wireless Telecommunication Systems, a talk given by Dr. Junaid Syed. The talk is the objectives of the talk is to understand what are the expectations of tomorrow's wireless communication technology, then how telecom demands are shaping the trends in the design of RF and microwave antennas in universities, R&D labs, and industries. And finally, what are the challenges and opportunities of design, testing, and manufacturing antennas, practical antennas that are useful to wireless communication systems. So the talk is given by Dr. Junaid, and before we get started with the talk, let me briefly introduce to you Dr. Junaid Syed. Dr. Junaid is currently the Senior Vice President of Corvolex UK company, which has developed phase array multi-beam antenna system and radio technology for fixed wireless access to provide high capacity internet connectivity to areas where optical fiber is not available. Dr. Syed holds more than 26 international patents, including 13 US patents, which are mostly in production, and thousands of those antennas have been deployed globally. Dr. Syed is a long-time veteran with an experience of more than 35 years, an expert in microwave antenna design, teaching and research, manufacturing, wireless communications development, and innovation commercializations. A passionate researcher, he's a true passionate researcher, teacher, technologist, strategist, and senior executive with ability to create a link between industry and academia, a link between theory and the practice. So Dr. Syed worked actively as member of the standardization body, international standardization body called ETSI and FCC for more than 10 years to assist the development of new regularity standards for antennas. He has been actively involved with key mobile operators in US, Europe, Middle East, Asia, and Africa to assist their transmission teams for modernization of their network. Dr. Syed also worked as Associate Professor at National University of Science and Technology, NUST, and Associate Adjunct Professor at Michigan State University in USA. Dr. Syed's teaching and research interests include antenna design and propagation and mobile and satellite communications. Earlier, he was also leading the microwave business of Comsom Company in Middle East, Asia, and Africa, and the global microwave business of Fressenberg, which is a very big global company specialized in the microwave and antenna design field. Dr. Syed was leading the design team based in UK, USA, and China for world's biggest microwave antenna supplier, which is Comsom. He established microwave antenna design center and testing facilities in China while working in a German company which has global presence, Rosenberg. Dr. Syed received his PhD from University of London, UK, and his postdoc in Queen's University, Belfast. So thank you, Dr. Syed, for joining us to share with us the recent advances in future RF and microwave antenna. Such an impressive experience, truly. And we are really honored to have you today with us. And with having introduced you, now the floor is yours and you can get started. Thank you very much.
Thank you very much, Professor. There's echo here. Maybe if can mute it. Can everybody mute, please? Okay. I hope now you can hear me and there is no echo. So first of all, thank you very much for having me here. In fact, about a month back, I was visiting Antalya on my holidays with my wife, and then I decided to visit your university. I had some communication with the professor earlier, and I came to your university for a couple of hours. I was really very impressed with the vision of the academia, the faculty member there, and also the head of the institute director. And I can see that you guys are in the right hands, and you guys are basically with those who have a clear understanding that the theory needs to be connected with the practical life. So when I found that, I thought this is the university where I should be engaged with. Uh, so that is the reason I volunteered myself, that I'm happy to talk to your students, your faculty members, and share the knowledge, my knowledge with you and your knowledge with me. It is a two-way communications. So as it was indicated in the introduction of me, that I am a guy who has been working in university and then in industry. So I'm always fond of connecting the theory to the practice. And I believe the work which you do in university is need to be applied in the real life. Because if the theory is not related with the real life, then it will just create frustration. There has to be an objective that the theoretical models, the equations, the algorithms which we learn in university, we should able to transform those equations into a product and a solution. And that is the most important thing in our life. So I will suggest all of you who are still going through the studies at university, keep that objective in your mind, that we need to deliver in the end to the real world and to the best of the community and the sciences. So that is the main objective behind here. Now, as the objective of the call has already been shared, so I'm not going to repeat it, but in the end, objective is to see what are the challenges and opportunities for antenna design, testing and manufacturing. Now, this presentation, which I'm going to use, is got a large number of slides, about 72 slides. Why I'm using this, that I'm developing a course, 1 day or 2 day course, basically, because few universities have asked me to do so. So I will not be going in a very depth. I will be basically flying over to give you a flavor in this 1 hour, so that you have an idea that where we are and where we are moving to in terms of the antenna. Uh, and if needed, then we can have some detailed 1 day forum or something else also. So I might be very fast in some of the slides, and I might be on the surface. I may not go in the depth, but I will, because each slide in this presentation need itself a 1 hour, 2 hour presentation. And I don't want to just stuck to one slide and then stay there. So objective is, if you see in a telecommunication world today, it can be divided into two halves. One is the satellite communication, other is the terrestrial communications. So in satellite communications, there are its own requirement. In terrestrial communication, it has got own requirement. But on a satellite communication has to be the wireless. And whenever there's a wireless, you need an antenna for a communication. In terrestrial communications, it can be wireless or it can be through the guided structure. When I say guided structures, I mean it could be through the cables or through the waveguides. Now, if you remember, in the terrestrial side, there are different options available for the communication from the physical layer point of view. The oldest physical layer which is being used in the world was a copper wire. There are millions or tons of copper wires buried all over the world, which was used for communications. And then the industry started moving forward, and they said that there are some restrictions with that media, that is the copper wire, for propagation point of view and from the demand point of view. So the research started on the optical fiber. Optical fiber is definitely a great invention of the centuries, and it opens a very wider road, very wider bandwidth to provide the connectivities. But at the same time, optical fiber is not possible or not available everywhere because of many reasons. And I will not go into those reasons. But anyway, I think we all are aware that why optical fiber is not there in a large part of the world. And there is still a need for the people, for the organizations, for the scientists, for the researchers, for the home, for a child, for everybody to enjoy the advantages of the communication. So in that case, the medium which comes in the mind is wireless. And when you talk about the wireless communication, the most important thing, I will not say the most important thing, one of the most important thing is the antenna design. So the antenna design is very critical for all satellite communication because it has to be wireless, and also for the terrestrial communication, because still a large part of the world is connected through wireless. An antenna is basically a device which enables these things. So antenna itself, if you think, move forward, I will just go to the next slide. Okay, so just to give you an idea about the telecommunication market today in the world. The current fixed and the mobile telecom market per year is about $1.7 trillion. This is the market size in this today, which include the satellites and also the terrestrial communications. There are 4 billion users all over the world who are connected and utilizing the telecommunications, but still there are 3.2 billion people on the globe who are not connected, who don't have the internet facilities. They are not in that tier where we are enjoying. So if you think 3.2 billion people are still unconnected in this globe of the world, and most of those people live near equator because of various reasons. You know why this connectivity problem is there near equator, because of the financial constraint and other reasons. And even in the modern world, in Europe and US, you will still find people who are not connected on the internet, and you will not be surprised. So if you look at the scope of the market, it is huge. Still, there's a lot of potential there to have a connectivity problems. So first, some people don't have the connectivity, so they need connectivity, and some people have the connectivity, but their requirements are not met. They are looking for some more parameters to move forward. Now, keeping in view this market size, right? Now, our all research, our all development, our all coursework should be focused to basically address this target addressable market. And that is where we have to focus. So we need to know what are the real problems and what are the real challenges and where to focus, so that when we are doing our coursework, when we are selecting a master's level project, or when we are doing a PhD thesis or a postdoc, our research should have an objective that where I'm going to apply that. Now, moving forward to the antenna technologies. In this talk, I have divided the antenna technologies in different application sectors, in different use cases. The first one is the mobile cellular access antennas, and these are called base station antennas. And the base station antennas look like this. So these are the antennas which are providing the connectivity from a base station to your mobile phone. So this is itself a big industry of the base station antennas. The biggest manufacturer of base station antenna today in the world is Huawei, Ericsson, Nokia, Siemens, and also there are some Chinese companies also which are very active. And those are the main players who are developing these base station antennas. The second category is the backhaul antennas. Backhaul is basically the connectivity of the base stations together. Now, backhaul can be divided into 3 categories. One is called front haul, second is called short haul, and third is called long haul. Now, in the backhaul, front haul is basically the connectivity when you have on a base station an RF unit, but the IF unit is somewhere else. So this is called the remote radio head is sitting at the base station, but the baseband, the BBU is sitting somewhere else, and you need the connectivities. This is a very high data rate connectivity, and mostly optical fiber is used in front haul. But where optical fiber is not available, people are using wireless. And since it needs high capacity, so you need higher bandwidth. And since the distances are short, so the ideal is the millimeter wave, which is 80 gigahertz or 60 gigahertz being used for front haul. And the antennas need to be designed accordingly. The second is the short haul. Short haul are basically the small and reflector antennas, which if you go out in Antalya or anywhere else, you will find these type of antennas on a rooftop or on a tower, and these are connecting different base stations and base station to the your main exchanges. Then the third is called the long haul. Long haul are these antennas, which are very big antennas. And these antennas are there to provide the connectivity for few 50, 60, 100 or 200 miles. And these antennas are basically connecting between cities. So if you see, the short haul antennas and the front haul and the long haul antennas have got a different design here. Maybe I will go future sessions about the design aspect, that what needs to be kept in mind while designing these antennas. But something is very obvious. If you see this antenna, this is a deep dish with no collar on it. This collar is called shroud in the antennas. But if you see the long haul antennas, they are shallow dish, not that deep, but you are keeping a shroud over here and a radome here. The purpose of this shroud is basically to reduce the side lobes so that you can use the spectrum more efficiently. I will come to the spectrum issue in a minute. The third sector is the public, private, enterprise, and defense antennas. This is a big demand where the companies need to be connected together. You need wireless connectivity in the police, in army, in air force, in navy. You need the connectivity of the offshore oil rigs with their offices and connecting those oil rigs. You need the connectivity for the bank. You need the connectivity for the custom. You need the connectivity for the border controls, and all these things needs dedicated connectivities, and these are other requirements. So the antennas which are designed for the public, private, enterprise, and defense have got different KPIs, different design parameters, and those need to be addressed. The fourth category is the fixed wireless access. What is fixed wireless access? This is the area where I'm working these days. I have worked in all these sectors basically, in all the 5 sectors, but these days I'm working in these areas. So fixed wireless access is basically, as the word suggests, that you are giving access to the fixed location. Here you are giving access to the mobile location, the mobile phone, but here you are giving access to the fixed location. And what is fixed location? Fixed location is the home, your offices. So there are large number of houses and homes and companies, offices, which do not have optical fiber. And one way is to connect their mobile phone and then create the hotspot there and have it. Other approach is that you provide direct connectivity to the home, wireless to home. As you know, fiber to home, similarly, there's a wireless to home also. And wireless to home is provided by fixed wireless access. I will talk about this also. And the last category is the satellite communication. It is itself its own universe. The antenna designs point of view. Even the full courses are available for the satellite communication antenna design. I've been offering these courses also earlier in the past. And in the satellite communication also, you can divide into 3 categories. One is the geo, which is a electrical orbits, the satellite which are very far from the Earth. Second is the MEO, and third is LEO, low Earth orbit satellites. I will talk more about this when we will move forward. Okay, so before we move forward, I thought we should just refresh our basic antenna 101 theory. Because our basic theory should be very good. Only then we are going to understand the antenna parameters and the antenna challenges and those type of things. Any question by anybody so far?
Yeah, thank you. Thank you for asking for questions. There is a small issue here. We are stuck at slide number 2. We cannot see the slides you are talking about.
Oh, you can't see this slide, which is slide number 5?
No. We can see only slide number 2.
Oh, sorry for this. I think this is the problem now. I know.
Okay, now we can see. Now we can see.
Yeah, I think I duplicate slideshow. So now I think it should be okay. So yeah. This was the okay. So slide 2 was this, and this was slide 3 where I was showing different types of the antennas. The base station antennas, the backhaul antennas, the public sector enterprise, fixed wireless access, and satellite. It is cutting from the site. I don't know why. So this is where I was talking all about the different types of the antennas and those things. And then, then I moved to the antenna fundamentals. So any question on this one?
So it seems so far so good.
Okay, go ahead. Feel free to speak out if you want me to stop anywhere. Okay. Okay. So I will go through the basic antenna fundamentals. So first of all, remember those guys who have been playing a very vital role for the antenna developments in the world. So the story definitely start. Many people were there, but I will say Maxwell is the person who is the father of the mathematics of the electromagnetics. And till the time mathematics is not strong, no design work can be done. So if you guys are studying mathematics, I was having this problem when I was in university that many students were not sometime interested in electromagnetics and antennas. And the reason is they say that this is very mathematical, very dry subject. We don't understand. You are talking about these equations, curl, divergence, gradient. We have no physical understanding of those things. And that is the dilemma. The dilemma is mostly the people who are going through the mathematics, they might not have gone to the real life application of that mathematics. But I can tell you, based on my 40 years experience in university and antenna design and industry, this mathematics is very important. Until and unless you will not understand the physics of this mathematics, the concept of this mathematics, you will not able to do really some innovative work. And the moment you understand the mathematics, you will see the world become very simple. And for that, the credit goes to Maxwell, who basically developed those equations, which we still use called Maxwell's equations. Then Hertz, who did the first dipole antenna, Hertzian dipole antenna, lambda by 2 antennas, a wire antenna basically. And he showed a communication at a distance of about 8 wavelength in his first antennas. And that was the place where the people start seeing the energy can radiate a wire and can carry the message, and we can receive it at certain distance. Hertz also was a mathematician. He also simplified the equations which were earlier done by Ohm's, Kirchhoff's, and Columbus. Then this guy, Alexander Popov, who's a Russian scientist, he showed basically a communication over the sea. And what he was doing, he had a transmitter in the sea, and he was having a lab in Russia in Petersburg. Any one of you who have seen Petersburg is a beautiful place. And he shows a connectivity through the wireless telegraph basically in 1895. Then comes the father of radio, Marconi, 1901. Marconi was a person who showed the wireless connectivity over a very long distance. And what was that long distance? He had one station in England near Cornwall, and he has other station in Canada. And those guys who know what is between Canada and England, that is the Atlantic Ocean. So he basically showed a connectivity with the over the Atlantic. Marconi used a very interesting antennas. He used wire antennas. Basically, the wire of about 200-meter length. He basically make a kite type structures over poles of about 60 meter. The pole which he used were not metallic, but were wooden. And then he used those 50, 60 antennas on top of that. And he used an array of that antenna for the connectivity. So this is how, if you see, the antenna started from a dipole, and then with the many dipoles or many wires, and then started moving forward. So after that, people started using the antennas, and at that time, most of the antennas were being made either with the wire antennas, a dipole or a monopole, or a loop antennas like those. And when the world entered into the Second World War, when they entered the Second World War, then one of the biggest technology which was on demand was a radar. And the radar technology gave birth to the reflector antennas and all those things, research in that areas. And once that was going on, and communication was, so the radar antenna technology moved to the wireless communication antenna, also for terrestrial. And then an era came for a satellite communication. When the era came on satellite communication, that was an era when I did my PhD, and my PhD was basically designing antennas for satellites at that time, for satellites which are in the low Earth orbit, and you can put those antennas on a satellite and which can illuminate the Earth, and you can change the footprint and dynamic beam shaping and all those things. This is I was doing in millimeter wave dynamic beam shaping in 1990. Right? And today we are talking something similar for 5G and 6G. So you see how things evolved over the passage of time. Okay, so the basic concept, what is an antenna? Antenna is just a transition device. A transition device between what? Between the guided structure and the free space. So you can transform energy You can transmit energy, you can move energy from a guided structure, which could be a metal structure like a hollow pipe, which we call waveguide, which could be a wire. And what you want that the energy which is inside the guided structures should able to come out to the free space, and similarly should able to go inside the free space. And this structure, which is, so it is a transducer in a word, is a transducer. If you see, I say something, everything in this world is antenna, and sometimes people laugh that you are in antenna world for 40 years, so you see everywhere antennas. Even your eye is here, right? Your eye is an antenna for the optical frequencies. And you are basically the guided structures. And what is the guided structures behind your eyes? Those nerves. And what are those? Those are the wires, those are the waveguides. And then it is going to the transmitter, which is your mouth. And then it is going to your receiver, which is your mind. So basically, your eyes are also acting as an antenna. Similarly, your ear, which is at the acoustic frequencies, of course, not on the electromagnetic frequency, but a similar mechanism is going on there. Even if you touch something and you feel something hot or cold, there is basically a wireless connectivity with your whole. So the God, Allah has made everything in your body, such an antenna which nobody else in the world has made it. So if you think from that point of view, definitely antenna is a field which is very interesting. And people who do antenna, they say that it is not just a science, it is an art also. And you enjoy artwork also when you are started working on the electromagnetic wave propagations and the antenna designs. So take antenna design as a patience, and I think this is something which you will definitely enjoy if you enter into this world. So from the antenna fundamental point of view, sometimes people connect the antenna with the basic circuit theory and can make a Thevenin equivalent circuit of the radiating elements. So basically, if you see, you have a signal source has got its own impedance, and this whole signal source is connected to the transmission line. This transmission line can be a copper wire, can be a parallel plate, can be a waveguide or any structures. And then you have another structure, this is the antenna. And what antenna is doing, antenna has got some losses inside, antenna has got some reactive impedance on it, and antenna has got some impedance which basically is responsible for radiating mechanism. So if you want more radiation, you want more RR rad. If you want less attenuation, less losses, you want less RR, the ohmic losses. And if you want more real energy, not the reactive energies, then you basically want to play with the impedance, with the imaginary part of the impedance. So, and you want the energy which is coming from a transmission medium, maximum should go inside. And similarly, the energy which is going from the antenna should enter in the transmission line. So which means there should be good handshaking. And that parameter is called the return loss of the antennas, the mismatch. If there's a mismatch between transmission line and the antenna, then definitely most of the energy will go back. And what will happen? Your radiation will reduce. And not only the radiation will reduce, if the energy will go back, it may destroy your signal source also, right? And if you see, I can explain the Thevenin circuit to the 5G and 6G also level, because if you see from this point of view, from a 5G and 6G point of view, what you need higher capacity. Higher capacity, you mean higher energy power, higher signal level, right? Higher signal level means you need to increase this thing. And if you are using a digital radios these days, in the digital radios, you are getting the signal in terms of the pulses, right? And if there's a mismatch, what will happen? These pulses will go back. When these pulses will go back, then that is called the echo. And when they will have the echo, then you will have the interpulse modulations. When you will have the interpulse modulation, that will go as a noise. So what will happen to the noise? The noise level will go up. When the noise level will go up, your detection power will reduce. When your detection power will reduce, your basically ability to discriminate wanted against unwanted will reduce. Hence, your capacity will reduce. So you see, somebody who's teaching Thevenin circuit has never thought about it, that how it is connected to the 5G and 6G. But if you have worked in theory and also in the real life, you can see all this is connected to the real world. And similarly, if you see the guided structures, very well explained this antenna radiation mechanism. Those of you who want to understand how antenna radiates, look at the book of Balanis, which I was using earlier for my coursework with the students. And this is something which is explained very well by him, how antenna radiates when the electromagnetic waves travels, how the polarity is changing and how the energy detach itself from the structures and then move forward. And first it is reactive and real both, and as it moves forward, it becomes mostly the real. And that is the concept of the reactive near field, and the far field. So all these things, and basically, if you see what is an antenna, I say antenna is just a camera. And what you do in a camera, you always focus at infinity if some object is at a far distance, right? And antenna also, you focus it to the infinity. And when you focus it to the infinity, what you want? You want the energy should converge at infinity. If the energy should converge at infinity, then how these rays should be coming out from this aperture? They should be parallel. So if the energy is more and more and more parallel, then definitely you are going to get more and more the energy which is in the far field. So when it start with a sphere, right? It remains a sphere till the end, but when the sphere radius increases a lot, then a small portion looks like a flat, and that is called the plane waves. And that is what we want. That is what we want for our wireless communications. I've done a lot of work with the communication with the spherical waves also, where the source and the receiver is in the near field. Sometimes we do that also intentionally, but in the wireless communication, we always try that antenna should be focused at infinity, which means that we should get the maximum flat phase, and that parameter of the antenna is called the phase efficiency. So when you're designing an antenna, you look at it, what is the phase efficiency of these antennas? There is another efficiency also, which is called the amplitude efficiency, that how effectively you are utilizing the aperture of these antennas. In theory, you want all the aperture should be illuminated with the same energy, so that you use the whole aperture. If you are using the whole aperture, then of course you are focusing the energy more in the direction. So antenna is not amplifying anything. Antenna is just a focusing device. So there is no amplifier here, right? So the energy which goes out is always more than the energy which comes out from this side, because some of the energy is lost in this structure because of the ohmic losses. So basically it is not an amplifier. It is a device which is focusing the energy, which is putting the energy in the direction where you want, and it is avoiding the energy where you don't want. And that is the basic function of antenna. Any question on this? No? Okay.
No, thank you.
Okay, so I don't think I will able to cover all the slides in 1 hour, but I will see how much we can do, and then we can have other sessions also. So the antenna types.
Feel free.
Sorry?
Feel free to talk as much as you want.
Yeah, because I have to go to another calls also. As I was telling you, today is a very busy day, but we decided to stay because the invitation has been sent. So I will definitely go as much as possible. Okay, so one type of antenna is the wire antennas, right? Wire antennas is a fundamental which I talked earlier when the communication started. So I have started with the Maxwell equations with a wire antenna, and I will finish on a 6G antennas. That is the purpose, right? So that we move around, that everything is connected together. Now, if you see the wire antennas, and these are, I think those of you who have learned electromagnetics are familiar with these equations. These are basically coming from the Maxwell's equations. And if you see, this is called curl of electric field. So E is the electric field and H is the magnetic field, and this is the electric current density, J. Curl and divergence. Any idea? Anybody would like to say what is curl and what is divergence? The physical significance? I want you guys to basically involve in this discussion. Anybody wants to say what is curl and what is divergence? No?
So I think the students are shy of answering.
Okay, no problem.
They want you to continue with the presentation.
Okay, okay. So curl, what is curl? When I was used to teach in university, people were really saying, I don't understand this curl, divergence, gradient, and electric field and magnetic field. They have nothing to do in the real world. The answer is no. It has a lot of things to do in real world. You have to understand it. So curl. So E is the electric field and H is the magnetic field. And as you know, we are talking about electromagnetics. Electromagnetic means it constitutes two types of field. One is the electric field, other is the magnetic field. Electric field needs electric source and magnetic field needs magnetic source. But if the electric field is changing with respect to time, it generates magnetic field also, and that is electromagnetics. So, and this why we call it a field, because field is a vector. It has got a magnitude and a direction, both. That is why it is called field. Now, once you have the field, so you have got basically two ingredients in this dish. One ingredient is the electric field, other is the magnetic field, which is E and H. Now, if you look at this, J is basically the imaginary part of it. W is your angular frequency, which is coming from the frequency from gigahertz and megahertz, which you can convert into W. This mu naught and epsilon naught, this is defining the medium that you are talking about, the propagation in which mediums. Remember, it was basically, I think it was Hertz who was talking about the wave propagations in different mediums and saying that in the free space, energy, electromagnetic waves always move with the speed of light, but once it moves in a dielectric, dielectric means a plastic or those type of materials, then it has got some properties which is called the permittivity and permeability, and the speed changes accordingly. So this is basically giving you the whole picture of propagation of electromagnetic wave in any material. The material properties are defined by these two variables, mu naught and epsilon naught. The frequency is defined by this omega, and the strength of the electric field is defined by E, and the strength of the magnetic field is defined by H. So we know what each parameter is showing here, the physical significance, right? Now, what is curl and divergence? Curl is basically, physically curl is the strength of rotation. This field can rotate and this field can flow. There are two phenomena can happen. Now, I will give you a very basic example. When you go to your sink, water basin, right? You open the tap. The water comes out of the tap and then it goes on the sink below. And if you see, there are two phenomena are going on. One is a flow. Water is coming out of the tap, and when it is hitting the washing basin, it is going below. And before going below, you will see a rotation of the water along that sink. And that is curl. So curl is the strength of rotation. If the rotation is more, you will say the curl is more. So it means the electric field can rotate also. And the strength of rotation of the electric field and the strength of rotation of the magnetic field is called curl of E and curl of H. Now, what is divergence? Divergence is the parameter and the KPI for the flow, is strength of flow. If the divergence is more, you will say the flow is more. So basically, under this configuration, it is telling you how electric field and magnetic fields are behaving when they are together as an electromagnetic waves in any medium. The medium has the properties of mu naught and epsilon naught, and the electromagnetic wave has a frequency which is corresponding to W, and it is telling you the strength of the rotation of the electric field, strength of the rotation of the magnetic field, and strength of the flow of the magnetic field. So these are three basic concepts. Now, if you look at a basic antenna, what is happening in the antenna also? The electromagnetic wave is coming out from an antenna. So basically you want maximum radiation out of it. So you can use these three equations and plus some more equations, and you can find out how much energy is coming out from these structures. And then you can start shaping that energy, that this energy should go in this direction, the other energy should go in other direction. But now the computational electromagnetic has advanced that much that you don't have to solve these equations. These are being solved by those mathematical simulation tools. So sometimes students become just a number crunching machine. It is very easy to put the numbers in. It is very easy to get the numbers out, right? And sometimes person has no physical idea what is the correlation between input and output. So I will suggest students, especially whenever you are doing some simulation work, please think about it, why it is happening. Link it up with the basic theory, with the basic mathematics. And once you are able to make that bridge, then it will make sense. Otherwise, you will just become a robot where you are just putting some numbers in and getting some numbers out. And it is your luck. You may get a solution, you may not get a solution. And until and unless you have real understanding of the basic theory, you will not able to give really a good design or something, a good product or a good solution which will fly. So this is very important, that don't just think that this is all useless. Nothing is useless. People are doing this for a purpose. And sometimes people say that I'm not going to use it in the real life. The answer is no, I'm being using this in real life. And as Professor mentioned, with this theory and with this bridge, I was able to get so many patents in the world, and thousands of antennas are deployed all over the world. And this is very important. And then you will have really the patience also. Okay, so the other antenna types are called the aperture antennas. I saw in your lab there is one aperture antenna with an 8 by 8 arrays. So why they are called aperture antenna? Because they have a phase and the energy is radiating from that phase. So if you see, this is an array antenna, and the array antenna could be from the waveguide or printed circuit board. Similarly, a reflector antenna has got an aperture. This is the aperture of the antennas from where the energy is coming out. And these antennas are also being used. So wire antennas and the aperture antennas are the two main categories. The other types of antennas also, the traveling wave antennas and slow wave structures. I will not go into those details, but if you just understand, you can divide antennas into two categories: wire antennas and aperture antennas. Now, antenna types, there are positives and negatives. For example, monopoles. What is a monopole? Monopole is just one half of the dipole. And dipole, the two wires you're exciting in the middle, where the monopole you're just exciting at the end. Monopole antenna is very simple. If you use in your car, the antenna, which is, I think I showed earlier also, something like this. This is a monopole antenna, basically just one side, right? Where if you see, they are the dipoles, but they are in an array form, and the length of the dipole is reducing in a such a way that you call it is reducing in as a mathematical trend of logarithmic scales. So these antennas are called log periodic antennas. If you see, this is also a wire antenna, but this is in a spiral, so this is known as spiral antennas. And these antennas are the PIFA antennas, which are being used in other countries. So I will maybe, but they are not, I think only the PIFA, they are antennas which are on the textile. So now there's a very big research is going on, which I have not talked earlier. And those are called wearable antennas. Antenna which you can use, you can wear it in your clothes. Those antennas are used for the medical purposes. And those antennas need to be made on a fabric, on a textile industry, right? And they have got their own properties, and they have got their own frequencies. They have got their own parameters. There's a lot of research is going on the wearable antennas also these days. I will not go to all these details and those things. If we get a chance and go for a detailed sessions sometime, then I think I will discuss these things. There's another antenna called fractal antennas. Somebody say, what is fractal? Fractal is a word which means the similar shapes. So basically you have a shape, you just have a periodicity of that structure. Because of the periodicity of the structures, you get some resonance and you get some similar, some behaviors. And those antennas are basically called fractal antennas. A lot of research is going on the fractal antennas. Metamaterials is another thing, which is a negative refractive index. You see when the light enters from one medium to other medium, it bends, and the bending depends upon the ratio of the refractive index of the two mediums. You must have done that experiment when you were at school, and a similar concept is used, and people have developed the artificial materials where you can bend the light in a different way, in a different directions. There are antennas which are called the antipodal Wilvedi antennas, which is very common, shown here for the E-band communication. E-band is the 80 gigahertz. Okay, antenna parameters, key parameters. Whenever we design an antenna, these are the parameters that are always in the mind of a designer, regardless whether the design is being done for research lab or design is being done for something to be deployed in the field, in the cities. First thing is, of course, the frequency of operation, that at what frequency you want to design an antenna. Then the second parameter is the return loss, which I just now mentioned. Return loss is how much energy is going to the antenna from the guided structures when they are talking to each other, and how much energy is not going inside. So basically, as the word says, the return loss. And you always want the return loss should be as low as possible. In industry, these days, the antennas which are used in the telecom market, generally the return loss is about 17 dBs or 18 dBs. In some cases, it goes to 14 or 12 dBs also. For the long haul communication, where you want most of the energy should go in because you are covering a bigger distance, the return loss can be 25 or 28 dBs also. So just to give you a feeling what return loss you're talking about. But sometime in the lab, if you are doing some new antennas, those people are just looking for 5 dBs or 6 dB return loss also as a prototype stage. Gain of the antennas. Gain of the antenna is the ability, it's not the gain of output power versus input power, because it is not an amplifier. Gain of the antenna is basically that how much energy you have concentrated in one direction from that structure as compared to another antenna if you give the same power to that structures and it is radiating equal energy in all the directions. So energy which is being coming all equal energy in all the direction, that antenna is called isotropic antennas. And if the antenna is such that the energy in the azimuth plane is same, but in the elevation plane, other plane is different, then that antenna is called the omnidirectional antennas. So generally the gain is defined with respect to the isotropic. So that is why the unit of the gain is not dBs. The unit of the gain is dBi. Means dB with gain with respect to the isotropic antenna. If I give this much amount of the power to my antenna and the same power to an isotropic antenna in one direction where I want the maximum radiation, how much more power will I get as compared to the isotropic antennas? So it is called dBi. Sometimes people say gain with respect to the dipole also, and then you say dBd. But generally in industry, gain is generally used in dBi. Return loss is generally used in dBs. I hope you guys know the difference between dBs, dBi, dBd, and dBm. All are the ratios. dB is a ratio of the two numbers. When you say dBi, it means you are still having a ratio of two numbers, but in the denominator you have a reference, and that is isotropic. If when you say dBd, it means again it is the ratio, but the denominator is the gain of a dipole. So gain is generally measured in dBi, dBd, or dB. But power is also measured in dBs, but there you say dBm or dB watt. And in that case, the denominator is either a 1 milliwatt or a 1 watt, right? So we need to be very clear in terms of the dBs and dBis and dBms. Sometimes people get confused on it. Beam width is basically the directional properties of an antenna. Beam width means you are radiating maximum energy in one direction. As you will go off the angle, the energy will reduce. So generally, when the energy become half, which means called a 3 dB, that angular width is called the beam width and also called the 3 dB beam width of an antenna. Front to back. Front to back means how much energy you are transmitting in the front of the antenna as compared to the back of the antennas. The antenna which is going, the energy which is going at the back is definitely an unwanted energy. And that is why you always want high front to back ratios. Otherwise, your network will start getting a lot of congestion and a lot of interference, and they will talk in the base station will start talking to each other, which are back to back each other. So you don't want that they should talk to each other. You want they should talk to the user equipment, not with each others. So this is also very important parameters, even for satellite communication. For all the antennas, this is very important parameters. Cross-polar radiation pattern. Cross-polar and the copolar. You know, when you are transmitting the energy, it has got a polarization. What is polarization? As I said, electric field and magnetic field are the vectors, right? The orientation of the electric field is generally defined as the polarization. So the orientation of the electric field, so the electric vector, if it is, and what is the orientation of the electric field? Basically how the electric field is changing. If the electric field is changing in one straight line, then you say it is a linearly polarized antenna or linearly polarized signal. Now, if it is electric field is changing in terms of a circular direction, that it is moving forward, but the electric field is rotating also, then that is called circular polarizations. If the electric field is moving forward, it is rotating 360 degree, but the magnitude is also changing as it is rotating, then you call it is elliptical polarized signals. So polarization is basically the orientation of the electric field variation as the energy moves from antenna 1 to antenna 2. Now you have a two polarization, copolar and a cross-polar. Copolar is the polarization which you want, in which you want the signal should be residing. So it is unwanted. Cross-polar is something when you are generating, let's suppose a vertically polarized is a possibility some energy is going in a horizontal direction also, and this is unwanted. So the ratio of the vertical versus the horizontal polarization is called the cross-polar, and that is called the cross-polar discrimination. And when you look at the cross-polar radiation patterns, you will see it has got a different angular behaviors, and you don't want cross-polar pattern. So this is something unwanted where the copolar is wanted. Back lobe. Sometimes you have a main lobe which is in the front, but sometimes you have a back lobe also, because when the energy goes outside the structures, it converges again and comes in phase at the back, and you see a lot of energy in the plus 180 degrees and minus 180 degrees. I've got many patents how to suppress the back lobe in antenna designs. Those of you who can, they can Google and they can find out what I've been doing for the back lobe suppressions. I've been doing a lot of work for the front to back ratio also, and also for the copolar radiation patterns, and also here for the IPI. What is IPI? Interport isolations. So if you have more than one port of an antenna, then you don't want that each port should be talking to each other. You want this port should be isolated, and this parameter is called interport isolation. How much is the time? 52. Okay. Radiation pattern. What is radiation pattern? It is basically the spatial distribution of the energy in a 360 degrees. And in the radiation pattern, you have basically how the energy is coming out. If this is the antenna, then the energy, more of the energy is coming in a form of a lobe, which is called the main lobe, but some energy is coming on the side also, and this is called the side lobes. There is some area where there is no energy coming, that is called the nulls, and the energy which is coming at the back, this is called the back lobes. So this is a typical antenna radiation pattern. If you want more directive antennas, of course, it should be more narrow. At the moment it becomes more narrow, the gain of the antenna increases. So the gain of the antenna and the beam width are related to each other. Higher the gain, less is the beam width. In some antenna designs, there is another factor is important, which is not in telecom for remote sensing and radiometry. I will not touch that. There are some basic equation, how the directivity of the antenna is linked up with the size of the antenna. This is the effective aperture, not the physical aperture. If area which is really contributing for the radiating, and this is coming from the frequency of the antenna, and then you have a directivity. Directivity is one parameter, gain is another parameter. Directivity is telling you how much antenna is directive, how much antenna is basically transmitting energy in that direction. Gain also tells the same thing, but directivity is always higher than the gain. And the ratio between directivity and the gain is called the efficiency of the antennas. And from why the gain is less than directivity, because there are some losses in the structures, and those losses, if you just include the losses in the structures also, then you get the gain. So in real world, when you measure it, you measure the gain. When you do the simulation, you get the directivities. So directivity is a parameter which is computed. Gain is a parameter which is measured. Right, and you can have an analytical formula for the half power beam width also. If D the size of the antenna, just 65 multiplied by lambda D, you can get the half power beam width. So there are some analytical formula, very basic, very simple, to give you an idea that what will be the gain of this antenna and what will be the beam width of these antennas. Now moving forward, this is all about the antenna 101. Now moving forward, we want first of all mobile cellular networks. We want antennas for mobile cellular network, starting from 1G to now 5G, and very soon 6G is coming up. If you see from this trend, definitely there is a need to have a new spectrum. There is a need to have a new technologies, because I started with the Maxwell equations and dipole, and now I'm moving forward to the massive broadband Internet of Things, holography, and also for the visual high resolutions stuffs, video gaming and all those things, and the medical industry, drones and all those applications. So we need to move from the basic Maxwell equation dipole to these type of antennas. So one thing is the new spectrum is coming, just to give you an idea. I'm not talking about 3G, 4G. And if you see what is changing here, one of the parameters changing is the capacity. So what is the main driver for all these G's capacities? The story started with the 2.4 kilobit per second, and today we are talking about 1 to 10 gigabit per second per user. And this is called the gigabit networks. There are many projects going on in different countries for gigabit networks to provide the higher capacities. Now, in this case, of course, what will the capacity requirement for 6G is still to be defined. But to do all these things, people are looking for the new spectrum. New spectrum means new frequency. Spectrum is a very, very scarce resource, very expensive resource, not very easy to get even. Not only expensive, but the problem is the availability also. I was doing a project. I remember those of you who have gone to Makkah for Hajj, they might have seen that how many people are there in Makkah, and they all are using the mobile phone, right? And when they all are using the mobile phone, what is the data rate requirement, the cumulative data rate requirement in Makkah area, just in those 4, 5, 6 square kilometers areas? And and of course, you are not, you need the backhaul also to provide the connectivity of those mobile phones. Now, the spectrum is very small, right? And how can you put all those data, all those calls in those channels of the backhaul so that you can get the maximum throughput from that areas. And there we did some work for the antennas, and we put some different types of the antenna in Haram Sharif, which was designed by Comscope basically. And the simulation work was done in Egypt at that time. I had a team based in Egypt for the network planning, and the team based in Scotland were designing the antennas. And there were some guys in Saudi Arabia who deployed it. So I'm just giving you one example, the real life example for the spectrum. If you see, the 4G was mainly focused till 6 gigahertz. Now we are in the 5G. 5G has gone up to, people are talking about 110 gigahertz in 5Gs. And very soon we will be hearing the 6G, where people are talking about a terahertz. Terahertz is 3000 gigahertz. And definitely, as you go higher on the frequencies, what happens? The size of the antenna will reduce. The propagation losses will be more. Hence, the link distance will reduce. If the link distance will reduce, what will happen? You need more antennas, more hops. So what you are seeing in the world, you are going to see from antenna point of view, with the passage of time, the size of the antenna will reduce. With the passage of time, the frequencies of the antenna will increase. With the passage of time, the number of antennas deployed all around you will also increase. And this is where the whole world or the whole globe is moving forward in terms of antennas. Okay, now 5G demands. Those of you who are doing research on the 5G, I have seen some of the work which is going on 5G in your universities. They are already aware of it. You know that what are the requirements, and these requirements need to be addressed by the antenna designers also. They have to keep these things in mind, especially if you think from the frequency point of view, it is very important what frequencies we are talking about. So in 5G, we are not using only sub 6 gigahertz, which is a 4.4 gigahertz, and those frequencies, people have gone to the higher frequencies also, and that is basically 26 gigahertz, which is mainly starting from 24 to 32 gigahertz, and also for 42 gigahertz also. And these communication technologies, which is on this frequency band, is generally FDD, frequency division duplexing. But for the millimeter wave 5G frequencies, the system will be TDD, time domain duplexing, and that is also an impact on the antenna designs. In the TDD, in FDD, maybe you have one antennas for the transmission and reception, but in TDD, sometimes you need two antennas separately, one for the transmission, other for the reception. And when you have two antennas, then the challenge comes that these antennas should be talking to the world, but should not be talking to each other. And that is called the mutual coupling. So another research area is how to put the two antennas closer together so that they don't talk to each other. The research areas people are talking about are metamaterials, shielding, and different other technologies so that they reduce they suppress the interaction of the nearby antennas. And that is a problem which is called antenna zoning or antenna farming. A lot of research is going on in that directions also. Apart from those, the other thing is the latency is also very important, especially for the medical facilities and those things. Now people are talking about the active antennas, and when you're talking about the active antennas, there are amplifiers, other things, and everything takes time. There's a signal processing going on. So the signal processing time is also becoming very important. And now antenna is not just a radiating aperture or dipole. Antenna is much, much more than that. Maybe in the last slide, I will show you that what all antenna design included. So what is the telecom demands today? 5 C's. Capacity, higher availability of the capacity. As I was in the university, I was discussing with one of the student who was doing some projects about the cell edge coverage, increasing the higher availability of the capacity, and it looks to me the concept was very clear. You see, the important is not the capacity, the importance is the higher availability of the capacities. I will not go into those things, otherwise I think I will use a lot of time there. Coverage is large. You need more and more and more coverage, and capacity and coverage goes against each other. If you increase the capacity, the coverage goes low. If you increase the coverage, the capacity goes low. So basically, a best design is such that where you have a good capacity also and good coverage also. And that is the trade where the designers need to look at it in the university and the R&D lab and in the industry. Compact, a small footprint, very important. Do you know what is the cost of an antenna to install or to put it on a tower? Not once, but for the monthly. When you put these antennas on a tower, there's a big industry, and that industry is owned by the tower companies, and these tower companies hold these towers. So what is their business? They make the tower and make available to the mobile operators like a T-Mobile or Vodafone or those. And they say that, okay, you can put your antenna on my tower. I will charge you this much. Any idea how much they charge? Huge amount. In US, it is about $100 per fit per month. This is out, I'm talking about 5 or 6 years back. Now it might have increased. So how much money is supposed to go from the operator side to give it to the tower companies to install the antennas? So what is best from operator side? To have a smaller size antennas. So they can put those smaller size antennas on the tower. But once you will increase the size of, when you will decrease the size of the antenna, what will impact? The gain of the antenna will impact. So what is the challenge? High efficiency antennas have a smaller size but more gain. I have few patents and I think I will talk about those, how that problem can be overcome. Complexity, interoperability. Now there are many companies, right? Huawei, Ericsson, and those things. As on a signal processing, I've seen some of the work I think going on the Open RAN in your in your department. That is one area which is very important, which we are also using for our radio designing team. And all those things are basically needs to be understand. And not only this, now up till in the 4G, the antenna was alone as compared to the radios. They were not designed together. But in the 5G, when you are going to the MIMO antennas, antennas and radios need to be designed together. So it needs to have interoperability between the radio and the antenna. And that is a very big challenge, that you can't swap the antenna with the radio with anybody. But with 4G, you can do it. But with the 5G and those things, that will be a challenge. The antenna will be designed for a specific customer, not for the open market. So this is another thing which is definitely important. And for interoperability, the more important thing is the regulation, the standards. The standards are not available at the moment, and that is what is basically causing the problems also. Let me see, I think I have another call. Sorry, let me see when is my next. I'm just checking my calendar. It's 1 o'clock. If I have some more time. Yes, I have got 10-15 minutes more. Okay, so I think what I will do, I will move fast now. I will not go into the details. Maybe it will just give you a flavor, and then we can have other sessions if needed, detailed session, because everything needs a lot of time and really if you want to understand. So base station antennas, this is the mobile cellular access antennas. If you see the 5G wireless antennas, so the objective is to provide the connectivity from antenna to this mobile phone. And not only the mobile phone, to some areas where you can have the hotspots and for the traffic furniture on the roads and all those things. So now again, I think if I will go into this, I can spend the whole 1 hour on this integrated wireless access solutions. I will move forward. So the trends are in the telecommunication, increasing the data transmission speed and low latency, more devices with improved quality of service. So on terms of the antenna, as I just now said, small antennas, more antennas. Antenna installation will be closer to the crowds, to the end users. Earlier, the antennas used to be on a tower, not very close to you. Now antenna will go close to you. Now this will raise another issue, health and safety issue. There's a big community who keeps working that antennas are causing problem. You might have seen a lot of activities were going on when the COVID started and the 5G started and all those things. I think it was just useless campaign. I don't see there is any link between those. But anyway, we need to make sure that the radiation should not be hampering the public. And this is why antenna installations and those things need to be kept in mind. In Europe and USA and these countries, it is really taken care of. But I have seen some of the Asian countries where putting antennas, big high gain antennas, and their people are putting in their apartments windows and they are just having a bed and sleeping there at the back of the antenna. Sometimes they are just sleeping in front of the antennas, high gain antennas. So definitely that is a silly thing to do. There are effects of electromagnetics, and those are ionizing or non-ionizing. Ionizing effects are not very well known. Non-ionizing is more known, and non-ionizing basically cause heating of the issues and all those things. Maybe I will leave that topic separately, but as far as you don't sit in front of the high gain antennas, you are okay, don't worry. And every excess of everything is bad. I think that is also very important. Base station antennas, one is the LTE, which is a 4G. Basically, if you see, this is the antenna looks like from inside the base station antenna. If you open it up, you will see they are the dipoles. And why they are at 45 degrees? Because the energy which is coming out or is communicating with this antenna is a 45-degree dual polarized antennas. So they are basically having a dual polarizations because of the antenna handset can be in any directions. And if you see, these cables are exciting, so there are 4 columns in this antenna. Each column has got number of elements, and each element has got 2 dipoles which are at 45 degrees, and you are exciting them from a one port. So there is basically a feeding network. Just a cable is running behind this, which is making sure the right amplitude and the right phase each element is excited. Now the number of columns decides how much what coverage do you need in the azimuth direction. If you have more and more columns, your beam width in azimuth will reduce. Antenna will be more directives. If you have more and more columns in the height, your gain of the antenna will increase. So every antenna which you are putting on a base station has got some coverage and some length. If you want higher capacities, you want a narrow beam antennas. If you want a wider coverage antennas, then you want a lower gain antennas. The height will be lower, but basically this will be smaller. So the antenna design, the length and the width depends upon where you want to apply it. Are you going to do it for coverage, or are you going to do it for the capacity? And sometimes you do together. So the antennas are available with the I think 35 degrees, 65 degrees, and 120 degree coverage. 65 degrees intermediate, which gives a good coverage and capacity both. 120 degrees gives more coverage, less capacity. 35, 40 degrees gives more capacity but less coverage. So it depends upon how you are designing those antennas. And these antennas are used. There are frequency bands which are allocated either for TDD or FDD. From antenna point of view, these are the passive antennas. There's no amplifier in this, so it doesn't matter it's a TDD or FDD, but the frequency does matter. So that is what is to be done. The other thing is that the antennas are related technologies. The MIMO is coming up, which is the beam forming, and those, if time permits, maybe I will talk about MIMO. Very important from research point of view for antenna designer these days. The other thing is the trend is to have antenna which is a multi-band and multi-port. Why multi-band and multi-port? Because there are so many frequency bands and people don't want to change antenna when they move from 3G to 4G or 4G to 5G. So the antenna should be covering bands of different Gs also. And the other thing is which is called the remote electrical tilt, because when antenna is sitting on a tower, you need some tilt also, so the beam can look down in the area where you are interested, and that is called the remote electrical tilt. That is also very important phenomena, a feature, and a lot of research is basically going on in that directions. MIMO. Maybe I think I have a slide here for MIMO. I will talk about MIMO there. What are the basic, the key design parameter for a designer for the base station antennas? That how many number of arrays you want. Generally, these antennas have 1 to 5 columns, and their internal duplexing is used. Frequency bands are used as for the 3GPP is a standard body which define which spectrum or which frequency band is used, and if this frequency band is for TDD or is it for FDD accordingly. Horizontal beam width, as I just now mentioned, 35, 60, and 120. Physical length, as I told you just now, that it defines the gain and the beam width of the antenna. Other thing is very important, which is a PIM, passive intermodulation. And this problem with the FDD antennas, because in FDD antennas, you are basically duplexing in frequency. So you're using more than one frequencies. And if these frequencies join together, add together, you get the next component, the harmonics. And if these harmonics are in the band of interest, then that is called the unwanted signal, and that is called the intermodulations. And these are a passive phenomena, not an active phenomena. That is why it is called the passive intermodulation. And that what it does, it degrades, it generates a noise. When it generates the noise, then what happens? Your carrier to noise ratio degrades, hence your capacity reduces. So you might be having a very high gain antenna, but in the end, you're not getting a good capacity because of the PIM. Return loss, I've already explained. Port to port isolation, I've already explained. Polarization, beam width, front to back. Similar things basically are the key parameters. MIMO and CISO. So basically from a MIMO, CISO, and massive MIMO and multi-user MIMO, again, this needs itself, I think, a complete activity things, and I can talk a lot about this MIMO antennas because we are designing those antennas here. Objective is to improve signal to interference noise ratios, and you get it to the MIMO gain. Now in MIMO, remember the MIMO gain depends upon how your signals are correlated. If the signals are heavily correlated, you will not get the MIMO gain. So from antenna point of view, signal should be decorrelated. The correlation factor should not be very high. So one of the easiest way of non-correlated factor is transmit at the same frequency but two polarization, vertical and horizontal, so that you are getting two signals and they are not correlated. Why they are not correlated? Because one is vertically polarized and other is the horizontally polarized, and that is called the XPIC MIMO. So you are getting the MIMO because of the cross polar interference cancellations, and for those type of antennas, the cross polar discrimination should be very good. And as per my experience, if the cross polar discrimination is about 27-28 dBs, you can get a very good MIMO gain for a single user. Single user MIMO means only one user and you are achieving the MIMO, as the multi-user means simultaneously you are having the MIMO gain for many users. Massive MIMO is another thing which is getting a lot of attention now, which means a large number of arrays antennas. When I was in the regulatory body, the question come, what is the definition of massive MIMO? How many elements you should call massive MIMO? And I think there are some numbers, 64 or those, where you can start calling them massive MIMO. And massive MIMO, you can have a two-dimensional beam shaping in azimuth and vertical both, but massive MIMO and all those things are good for omnidirectional coverage or a sector coverage for the base stations. People are trying to use MIMO for the backhaul also for point to point, but that MIMO is really has not got a lot of attention because the signals are not correlated. And second, you have to put the two antennas at a very large distance. In that case, you need a very big tower to have that antenna separation. So MIMO is generally used for the antenna access, not for the backhaul at the moment. Massive MIMO, I think I will not go into detail, maybe its time is less. This is the frequency spectrum which is being used for the 5G in different parts of the world. Some are used in America, Europe, and other parts. Mainly the focus is 24 and 28 gigahertz these days. 24 is for Europe and 28 gigahertz is basically US, Korea, and Japan, which are getting, and 24 gigahertz is a lot of getting attraction in Asia also because this is WRC19 band. This is the base station antenna designing, how we do the designing of the base station antennas. If you are using the one array or two array or n number of arrays in that stations, and of course we need to give the right weight to the each element so we get the desired separation and the desired coverage. Huawei has got a good paper on it. The multi-user MIMO, so you are having more than one beam, maybe in this case 4 beams, so you're talking to the 4 users simultaneously. There are more than 4 beams antennas also available, and the massive MIMO antenna design has got its own design cycle, which include how you are going to excite that array and amplitude. And plus, not only this, you need some sensors also, sensors to detect the signal level, and also the heat dissipation, because they are generally the active antenna. So there's heat dissipation, a very big challenge in massive in these type of antennas. Phase array antenna concept. So basically you change the phase of the elements, and by that you direct the beams in the different directions. Phase array beam forming ICs. Now the integrated circuits have come. Instead of earlier you were using the phase shifters and all those things, analog beam shaping, or you are using the digital beam forming. But in digital beam forming, you are doing the A to D converters and all those things. Now the problem becomes very simple. You can have a beam forming ICs. Noki Wave and Renesas are the two big companies who are doing a lot of work, and we are also using these beam forming ICs now in our new antennas, which are we call the smart antennas or software defined antennas. We are basically, if you see in this case, this chip can excite the 8 columns, which means it can excite 4 elements like this, 2 polarizations, vertical and horizontals, and you can control the amplitude and the phase accordingly so that you can get the multiple beams as we are getting over here. You can get many beams. Multi-beam antenna has got its own challenges. If you see the tapering down of those things and the overlapping things, maybe if time permits, next time we will talk about it. And now the beam forming ICs are used generally with another IC, which are the up and down converter. So you use the baseband, up convert it, pass it to the beam forming ICs, and then send it to the radiating patches or horn or reflectors and get the desired beam. And same thing, you do it in a reverse path. And generally these are used in a TDD mode these days. Metamaterial is another very good area. I love this area. And metamaterial is those material which are artificially made. And how they are made? By using the pin diode, varactor diodes, and those things. What is a pin diode? Where you get the on and off action. And what is a varactor diode? Where you change the biasing and change the capacitance. Changing the capacitance means changing the resonance of the structure. Changing the resonance of the structure means changing the properties of propagations in that thing. And then you can shape, you can make a different shape, different size. A lot of work is going on the meta surfaces lens designing also, where you can get the phase shifting. And this is some of the areas. So you can have basically an array and passing to the meta surface lens, and you can have basically many beams and then transforming to very high gain beams here. This is one architecture. Other architecture is you have the baseband, RF chain, and you don't need an array separately. The meta surface itself is generating the beams. So you don't need these arrays to excite the meta surfaces. This is also being investigated. It is a good paper, 6G by Samsung. They are basically very actively strong in this. Rapid growth in 5G millimeter wave frequencies are basically 6 gigahertz to 24 gigahertz, which is getting a lot of attention now. Millimeter wave has got its own limitation, and that is the propagation losses. If you see the losses attenuation dB per kilometer, if you are moving this direction, it is a lot here because of the molecular attenuation of the atmosphere. And for the rain is another big problem. Sometime millimeter, not sometime. If the rain rate is higher, this is the rain rate, how strong the rain is. And if you see, if the rain is very strong, the attenuation at the millimeter wave goes very high. So millimeter wave solutions, 24, 28 gigahertz, very good, high capacity, but for a short distance. This is the lamppost antennas. A lot of interest is going on. I've got another patent on the lamppost where I did a lamppost and we did an antenna on the top. This was a millimeter wave E-band to connect the post with each other. So on a street, the lamp posts were connected together, and then there's a base station, this antenna base station, and base station antenna, we were using Ericsson at that time, and they are talking to the vehicles on the people on the road. And this is the radio over here, and the radios are basically coming from the radio supplier. So, and of course it looks like a lamp post, but in fact this is whole base station, including the access antennas and the backhaul antennas and the radios. PFA is another area which is the antenna design for the mobile phones, which is a planar inverted F antennas. Basically, in this design, we need to keep the size of the antenna smaller because all antennas need to be put in the mobile phone. And if you see, many antennas are going in the mobile phone. It's not only one antenna on the side. It's a Samsung Galaxy S design, which antennas are being used from 850 to 1900 megahertz. This is the antenna which is generally done for PFA antennas, which are for the mobile phones inside, and the radiation patterns. These can be a metallic structure or they can be on a printed circuit boards, PCBs. Antenna design for machine to machine and IoT, which is getting a lot of attention from 1.4 to 1.5 gigahertz. They are typically small sizes. They can be curved. So these antennas, the printed circuit board, the flexible printed circuit boards are also getting a lot of attention because of those. You might have seen some of the Huawei phones which are more flexible now, and people are using the flexible PCBs for designing the antennas. The challenges there is how to do the RF cabling and the connectors and the form factors. These antennas are generally linearly polarized with very high efficiencies. Backhaul antennas, these are the antennas which are used to connect the base station together. And then, hello, are you guys there?
Yes, we are there.
Oh,
but
you are not going to sleep.
The slides are not showing completely. We cannot see the full slides.
Yeah, I think it is cutting from the side. You're right. I don't know. It may be something wrong with the setting in my laptop.
Okay, no problem. I see that you are in a hurry also.
Yes, now I want to just scan it over, and maybe if we want to have, because this is the full coursework for 1 day or 2 days. So, okay. But I wanted to give you a flavor of it. Okay, so this is the backhaul antennas. Here I put some of the antennas which are being used in a backhaul. I've been designing this antenna for many years. And most of the patents were basically in these type of antennas, which are reflector antennas with a dual band, or the flat plate array antennas for the short haul, for the long haul, and all those things. And these antennas come in a different configurations, which you might have done in your Antenna 101 course. I will just go through some of my patents. So this is one of my patents, Syed, 2005, where I was doing the antennas with a very low side lobe levels to improve the C over I ratios. And you'll find millions of those antennas deployed all over the world. And I feel a lot of pride on this antenna because this antenna really became very favorite in the world when I did it in 2005. Earlier, before that, most of the antennas were like this, a shallow dish and a shield. But after the design of these antennas, you can see it's very compact and very good radiation pattern, and you can have a higher signal to noise ratios. For the long haul antenna, this is my another patent where I was designing the antennas shallow because the antennas were very big. So I was putting the shield over here. And if you see how much I was reducing the side lobe levels, this was the conventional antennas in the market at that time. And we did the antenna which gone below. So a big reduction in the co-pole. This is the cross-pole radiation pattern, and this improved the signal to noise ratios, and this improved the XPIC, which means the MIMO gain. So you are getting the both advantage, C over I improvement and also the MIMO gain. And jointly, if you use together, definitely the capacity will increase further. This is another antenna design, which is my another patent, where I was working more on the radome design, because radome is also very important, which is protect the antenna from the rain and attenuation, and also for controlling the energy scattering when the energy goes through this materials. This is another my patent where I was, you see, using the electromechanical devices, electrodes, which changes the capacitance, and we were doing the mount design for that. So what happens? When these antennas are on high tower, with the wind, these antennas sometimes shift left or right, and it is very difficult for somebody to go up and align the antennas again. So what I did, this patent I did in China, in fact, in 2020, not very far. Okay, so in this patent, what I did, I put basically some electromechanical device and some memory in it, so the antenna remembers where it is looking. The moment it shifts left or right, up and down, a signal goes from here and moves the antenna in the right direction. So you will always maintain the link on this one. I was very to be honest, very happy with this invention, because here I use this concept. I tell you, how did I get the concept? I went to a vendor who was doing machining work, and all the time his part was falling from the machine. And then he took me to the another machine where the part was always adjusting itself and not falling from the machine. I asked him how you are doing it. He showed me this sensor, that I'm using this sensor. I said, oh, why not I can use this sensor in antennas, and I can make sure the antennas remain aligned, especially in the difficult situations where you can't go up and realign the antennas. So this is another work which has been done. This is the work which I did in 2011. This is one of my patent where I made an antenna which is doing both operations together. This is the base station antenna and this is the backhaul antennas. Earlier, you see, everything is separate, but in this antenna, I joined them together, and sometimes people were calling it thermometer antenna also by Syed. And this antenna is basically having 28 gigahertz antennas over here, and I think the LTE frequency antenna over here. This antenna was designed for American operator Sprint at that time. This is another antenna which I did. You see that the other thing is the dual band, multi-band, as I said. So I designed this feed where the feed can work in more than one frequencies. If you can see, it's a coaxial design which has got a reflector here and a dielectric material here inside. So this is the antenna feeding to this reflector at 80 gigahertz, and this is the feed which is feeding at about 23 gigahertz. So if you want higher range, you can use. Basically, if you want higher capacity, you can use 80 gigahertz, but if the rain starts, then 80 gigahertz will not be very good. Then you can use the 18 gigahertz antennas. So this is basically that. This is another work where we were working on the designing of the side lobe suppressions and all those things work. Public defense antennas work. These are the antennas which are used to connect the enterprise market and those things, horn antennas. This is the future. Wi-Fi is also a very important area. Maybe if time permits, I will spend a couple of hours next time on the Wi-Fi and Wi-Fi antenna design and why it is moving from 2.4 to 5 and 5 to 6 and now 6 to 60 gigahertz. And I think everybody will be interested in the Wi-Fi because we all use Wi-Fi at homes. Fixed wireless access. This is the area where I'm working now. So basically the antennas are used. This is to provide the connectivity of villages and those places where the internet is not available. This is our new design, which we are doing it a phased array antennas, transmit antenna and a receiving antenna, and the radio is sitting here. This picture was taken in Philippines. LMDS is another area very old technology, but coming up again in America, where you are providing the base station directly connectivity, and this is called CPE, customer premises and equipment, and the base station antenna. So this is at CERT, and you can connect it to the satellite. So you basically go to that remote location to the satellite, then make a base station, and then transmit locally, and you can get a very good throughput in the remote areas also. This is different type of coverage which are used for the antenna design. For the cell point of view, this is the antenna which you can see my YouTube video on these type of antenna for the multi-beam antennas, which is on the Curvelex website also. And I am talking a lot about this, about the multi-beam antennas in the media these days. Satellite communication antennas, we are doing something like that also for GEO, MEO, and LEO satellites for different distances. These are the antennas. I was involved earlier for the designing of these antennas in earlier company. Now I've been working something different antennas for the LEO, low Earth orbit satellite. The challenge with the LEO is the antenna should be moving because the satellite is not fixed, and that is a challenge basically. This is the antenna payload antenna. So the company where I work, it has got another company which makes the satellites, and they basically wanted my help for designing of the antennas. But this is not my antennas. This is from the big companies, and they are already in the market. The Lundberg lens is another technology, lens antenna technologies, I think very interesting area, maybe worth talking next time. Antenna testing is another area which needs attention. Antenna testing trends, how antenna is being tested in different areas. There's a separate course I generally offer for the antenna testings. And antenna manufacturing, a very important area. How do we make antennas, right? I've worked many years in this field, so I'm sure we can have a separate sessions for antenna manufacturing. Also, these are the regulatory bodies which are important, and as you mentioned, I was member of these two main body at sea, which developed the standard for Europe and the world, FCC for America. Research areas, for those who want to do research, feel free to contact me. I can give some ideas, some areas, identify those things for you guys. And the antenna teamwork is not by the antenna design, it is antenna design, RF mechanical process, TSP engineer, embedded, RFIC, test engineer, quality. This is my team currently, which is doing the antenna designing. So basically we need to, if you see, it's a cross-discipline activities, not just one person is sitting there and doing all that work. Thank you very much.
So thank you very much, Dr. Syed, for the really insightful presentation. I'm really very impressed, and the same I think the other students and the other faculty members. But like you were really in a rush, trying to finish it at the end. We couldn't.
I think I was trying to cover 1 day, 2 day workshop in 1 hour. That was